All right, welcome to The Explainer. Today, we're diving into what might be the most famous equation in all of physics. And we're going to find out why. The version we all learned in school, yeah, it's just a tiny, simplified piece of a way bigger, much cooler puzzle. Oh yeah, you know this one. F equals ma. You've seen it pretty much everywhere, right? From high school classrooms to coffee mugs. Force equals mass times acceleration. It's simple, it's elegant, and for a long, long time, it really felt like this was it, a fundamental rule of the universe. But what if I told you that this super famous law is incomplete? That the equation we all had to memorize is actually just a special case of a much more powerful, more universal idea. Okay, let's dig in and see where this simplification actually comes from. Now, let's be super clear here. This law is a cornerstone of physics for a very good reason. I mean, it perfectly describes so much of the world around us. Think about a baseball being thrown or a car speeding up from a stoplight. In those everyday cases, yeah, it works like an absolute charm. So why does it work so well in those specific situations? Well, it's because there's this crucial assumption that's baked right into the formula, a condition that's kind of hidden in plain sight. And that hidden assumption is this, that the mass of the object never, ever changes. That little m in F equals ma, we're taught to treat it as a totally fixed, constant value. But you know, the universe, it's a whole lot messier than that. So this raises a pretty big question, right? Because in the real world, mass changes all the time. If the one thing we assumed was constant is actually, not constant, what does that do to our neat and tidy little law? I mean, just think about a rocket. Its entire job is to get lighter and lighter by shooting out fuel. Or, hey, even something as simple as a shopping cart rolling through the rain and collecting water. In these real-world situations where the mass is changing, all of a sudden, F equals ma just doesn't cut it anymore. To solve this puzzle, we've got to introduce the real hero of our story today. It's the concept that truly governs motion in the universe, and it's called momentum. Okay, so momentum, we use the letter P for it, is basically mass in motion. It's a way to measure just how hard it is to stop something that's moving. The more massive it is or the faster it's going, the more momentum it's got. You know, a bowling ball and a baseball can actually have the same momentum, but that baseball would have to be moving way, way faster. And listen, this isn't just some new variable we're throwing in here. It turns out that Isaac Newton's original big idea, it was all about momentum. He totally understood that there was something way more fundamental going on, and this is the idea that ties it all back together. Okay, this is where it all clicks into place. We're about to connect the simple law we all know and love to the bigger, more powerful one that's always true. This is it, folks. Newton's actual second law of motion. It says that a force isn't just mass times acceleration. A force is equal to how quickly an object's momentum changes over time. That is the real definition. So check this out. Here they are, side by side. The law on the right, force equals the change in momentum over time, that's the universal truth. And since momentum is just mass times velocity, this law takes into account changes in both of them. Now, here's the cool part. What happens when mass is constant? Well, the only thing left to change is velocity. And what's a change in velocity over time? That's right, it's acceleration. So this bigger general law elegantly simplifies right down into the classic F equals ma. So don't worry, your high school physics teacher wasn't lying to you. F equals ma isn't wrong, it's just a special case. It's like one law is a single perfect snapshot, but the other one, that's the whole movie. All right, so let's see this more powerful law in action with a perfect example, something that F equals ma just can't handle. Let's talk about a rocket. So how do you figure out the thrust of a rocket while it's burning fuel? Well, F equals ma can't help us here because that m, the mass, is constantly going down as it shoots out exhaust. We can't use a constant m. But the momentum law? Oh yeah, it was pretty much made for this exact problem. Okay, so let's picture our rocket out in space. Right now, it has a mass of 1,000 kilograms. But every single second, it's shedding 5 kilograms of that mass by blasting it out the back as exhaust at an insane 2,000 meters per second. Now, using our momentum principle, the thrust, the force pushing that rocket forward, is simply the exhaust velocity multiplied by the rate that mass is being shot out. We are literally creating a force by throwing mass away. So let's plug in the numbers. 2,000 meters per second times 5 kilograms per second. And that gives us a forward thrust of 10,000 newtons. And this just perfectly shows the power of using the correct law. We just calculated something that was completely impossible with plain old F equals Emma.
Yep, that 10,000 Newton force is what shoves the rocket forward. It's a perfect example of a force being created not by accelerating a fixed mass, but by actually changing the mass of the whole system.
So the next time you see F equals ma, just remember, it's a brilliant snapshot, but it's not the whole story. The real story of motion isn't just about pushing things. It's about the constant dynamic dance of momentum. And understanding that difference, well, that's what lets us go from calculating a rolling ball all the way to launching rockets to the stars.